think of this as what's good about singular value decomposition. Okay. And what we'll see is that the singular value decomposition allows you to get matrices that are simpler than your original matrix, but approximated in in the best way possible. Okay, so that is, they give you can create best approximations to your original matrix. Okay. Now, what does that mean, best? Best will be in terms of the Frobenius norm. So we'll call the Frobenius norm, which we saw earlier. I don't know if we named it the Frobenius norm, but we've seen it before. So the Frobenius norm of a matrix, so you have a matrix, and you take its norm, denote the Frobenius norm by putting a little f on it. And this norm is going to be the sum of the squares of the entries to the 1/2. Sum of the squares of the moduli of the entries to the 1/2. So I be sum over all I and j. So basically, this is, remember how you define the norm of a vector, right? You take the squares of the entries, you sum them all, and you take it to the 1/2. So this is basically pretending that the matrix is one long vector. Okay, it's just been arranged in a rectangular form. Okay. Okay. So the following lemma will be useful to us. If you have a matrix and you have another matrix which is orthogonal, okay, and it's square, of course, it's orthogonal. Then if you multiply your matrix by the orthogonal matrix and look at the Frobenius norm, then you see that nothing happens. The Frobenius norm doesn't change when you multiply something by an orthogonal matrix. Okay, and proof of this is pretty straightforward. Maybe I'll let you think about it for 1 minute. Okay, see if anyone can think of why this is true. Why doesn't anything change? Anyone have an idea? Teresa.
Oh, it's because the orthonormal means that Q is 1. No. There's something about the orthonormal 1 now. Squinty eyes.
No.
It's okay.
No. But okay, so think like this. You have your matrix, right? So you have your matrix A1, A2, rows and columns n. Right? And then here you have Q, right? What happens when you multiply by Q? What happens when you multiply by Q? Well, the Q applies to each column separately, right? So this is going to be QA1, QA2, Q blah blah blah, QN, right? Okay. Now, what's the so if we consider the Frobenius norm of QA squared, consider the norm of QA squared. Well, that's the right. So the Frobenius norm squared, right? You're just going to square all the entries and sum those things together. Right? Take the moduli of each entry and square it, and take the sum of the squares. Okay. Now, if we if we write it like this is going to be the matrix QA1, QAN. So you're taking this size of that thing, right? Well, that's going to be the norm of the vector QA squared plus the norm of the vector Q sub AN squared. Right, the Frobenius norm says the Frobenius norm squared means that you're going to take this, the absolute value of this squared, the absolute value of this squared, the absolute value of this squared, blah, 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 all the way down. If you look at that, what is that? Well, that's the norm of the vector squared. Right? That's the norm of the vector squared. Right? And so each column is going to contribute this. Right? And at this point, you use something about the orthogonality. Right? What do you use, Teresa?
The one.
The one. Right. So when an orthogonal matrix is applied to a vector, it doesn't change the norm. Right? We saw that earlier. Right? If you're looking at QA, right? Then QAI, well, this is the same thing as QTQAI, but it's orthogonal, and so this is the identity matrix, right? And so you end up with AI. Right? So applying, orthogonal matrices preserve norm. Okay, and so preserve the norm of vectors, and so we end up with this, right? A1 squared. Right? But that is the Frobenius norm of A squared. So applying an orthogonal matrix doesn't change the Frobenius norm. Okay, simple. Corollary. So what does this tell us about the singular value decomposition? So say A equals U sigma VT, right? This is the singular value. This is a singular value decomposition of A. Then, right, where E, you remember, is this matrix sigma 1 to sigma n above, and then 0, 0 below. Right, you've got the singular values going down in decreasing order. Right, so singular values. Remember the lambda, the sigma I are lambda I lambda, right, and we assume that the sigma i's are in decreasing order. Okay, so suppose that you have a singular value decomposition. What the previous lemma gives us is something nice, that the Frobenius norm of the matrix is actually the sum of the squares of the singular values to the 1/2. Okay, and the proof is pretty simple. You say, well, look, if we look at the Frobenius norm of the matrix, we use the singular value decomposition. Well, this is going to be U sigma V transpose. Right. And then by the previous lemma, it's okay to get rid of this orthogonal matrix, right? So by the lemma, we know that we can get rid of that view. Right? If I also, an easy observation is that the Frobenius norm of the transpose is going to be the same thing as the Frobenius norm of the original matrix, right? Because when you transpose it, you're still going to get the same entries. Right? So I can take the transpose. I can take the transpose without changing the Frobenius norm. Right? Because it doesn't change. The Frobenius norm is the square root of the sum of the square root, the sum of the squares of the entries. If the entries don't change, then the Frobenius norm doesn't change. Okay. And so this is going to be V sigma transpose. The Frobenius norm of this. And again, I use the lemma again, and notice I can pull the V off. Right? So I get that the Frobenius norm of the matrix is actually the Frobenius norm of this central bit, the central matrix in the singular value decomposition. Right? But the singular value, this matrix is this diagonal matrix on top of the zero matrix. And its Frobenius norm is that. So, yeah, and
why does the V disappear there in the last?
The same thing. It's an orthogonal matrix, and the lemma says it's okay that orthogonal matrices don't change the Frobenius norm. Right. So, left multiplying by the lemma says left multiplying by an orthogonal matrix doesn't change the Frobenius norm. I was right multiplying by an orthogonal matrix. I put a transpose on it to make it left multiplication. But you see by doing this trick is that, you see by doing this trick that, in fact, left or right multiplication by an orthogonal matrix doesn't change the Frobenius norm. So I should remark that. Notice we've shown that that you can right multiply by an orthogonal matrix, and that won't change the Frobenius norm either. So left or right multiplication by orthogonal matrices doesn't change the Frobenius norm. Okay. Any other questions? Okay. So now we're going to get to the problem. Okay, so here's the problem that the singular value decomposition is going to allow us to solve. Let's say that, again, A is an m by n matrix, and the rank of A is again denoted by R, as we did before. For k less than R, let M, let's say M denote all m by n, right, the set of all m by n matrices of rank less than k, less than or equal to k. So let's look at matrices of lower rank than A. And our problem is we'd like to find x in K, in M, such that A minus x in the Frobenius norm is minimal. So we would like to find a matrix, right, that's of low rank. Suppose, for example, you'd like to have a matrix of rank 2. And you have some very complicated matrix, and you would like to store a very low quality approximation to it, rank 2. Okay, so, and what we're going to do is say, can we find a rank 2 matrix? So in that case, we take K to be 2, and our question would be, can we find a matrix of rank less than or equal to 2 so that it's as close as possible to A, right? So that the difference between these two matrices is with respect to the Frobenius norm is as small as possible. Okay, so you take any other matrix, it's going to be at best just as good and likely worse. Okay. Okay. So that's the problem. We'd like to. That's the problem in those pictures in the application, right? Can you find a rank 10 matrix that approximates the photograph? Right? The photograph actually has it was 260 by 176, right? It has that much information in it, right? But you'd like to compress it. Yeah.
Is X not necessarily unique?
I'm not sure, actually. I'm not sure. I think it is unique, but I'm actually not 100% sure about that. So by the theorem, so let me put the theorem up, and you'll see that, in fact, it doesn't say that it's unique. But yeah, okay, yeah. So I'm not sure. We'll be able to solve it, but I don't know if it's unique. So let A, here's the theorem. Let A have a singular value decomposition. Let's say that A is U sigma Vt. If X in M solves the above problem, so let's call this problem star. If X is a solution to the problem, then the distance of X from A is actually going to be the sum of the squares of the singular values above K to the 1/2. Okay. In other words, this is the minimal distance to the space of matrices of rank less than or equal to K. I think it is unique. I think it's unique, but I'm not going to say why, but I think it is unique. But from this theorem, it doesn't say that. Okay. Okay. Everybody understand the statement of the theorem? You've got so this is saying if a solution exists, then the distance between A and that solution is going to be this. In other words, this is the distance to M of A, right? M, you think of this as space, right? A is some matrix, and you're wondering how far am I from M, right? And it turns out that the closest matrix in M is this far away, closest matrix is going to turn out, we'll see that it has to be this far away. Yeah, Henry?
Why was the k plus 1? Oh, rank k, never mind.
Yeah, so we're looking for the rank k matrix. We're looking for the space of matrices of rank k or less, and the distance is going to be this thing here. Okay. So the mark. If we let A prime be U sigma prime be T, where sigma prime is where you make sigma prime out of sigma by nulling sigma k plus 1 through sigma n. Okay. Then the distance from A to A prime let's think about the distance of A from A prime. Everyone okay with the creation of A prime? What we do is we take the singular value decomposition, right? We take the singular value decomposition of A, and we take this matrix in the middle here, and we set to 0 all the singular values past the kth. Okay. Originally, this has singular values like this, and then zeros like this. Right? This is sigma here. Okay. But we're gonna only take the first k, and then set the rest equal to 0. Okay. And that will be our A prime, and that will be a rank k matrix, or k or less matrix. So then A prime is an M, and if we look at A minus A prime's Frobenius norm, well, that's U sigma V transpose minus U sigma prime V transpose, the Frobenius norm of that, right? That's the same thing as U sigma minus sigma prime V transpose is Frobenius norm. And what we just said is that multiplying on the left or by the right, or on the right by orthogonal matrices doesn't change the Frobenius norm. So we end up with this. Right. But what's that? What's the Frobenius norm of sigma minus sigma prime?
That means this sigma's the armed.
But the k plus
Okay.
1. There's a k plus 1. So think about what that matrix is. Prime is and first prime, and then
Yeah.
when you subtract them, you get rid of the 1 to the right.
Right. What is it?
Oh, so it's 1. It's what you
Send it.
had up there before the
Oh.
square root of the squares of the k plus 1 to n.
Right. It's going to be sigma 1 squared.
Ah.
Sigma k plus 1 squared into sigma n squared. Right. Right. Because when you subtract, right, sigma is this, right? And when you subtract off sigma prime, well, you're just going to be left. You're going to be left with the only entries that are left are sigma k plus 1 through sigma n, right? And the Frobenius norm of that is this. So what does that tell us? That tells us that this thing is a solution to the problem. And I think the solution to the problem, right? It's with the theorem, right? The theorem says if a solution exists, then this is going to be the distance, right? the theorem says that this is the minimal distance to M. Right? And we notice that using the singular value decomposition, we can make a matrix which has that minimal distance. Right? So this is right. So this is the I think the matrix that is closest to A of rank less than or equal to K. Okay. We haven't proven the theorem yet, but we're just saying that assuming the theorem, we actually notice that the singular value decomposition allows us to create the approximation that we're looking for. Okay. Here's sort of an exercise, something to think about. Say A is square. Okay, suppose that A is square, and the rank of A is N. Okay, so it's invertible. Right? A is invertible. What's the minimal distance? What's the distance to the rank less than or equal to n minus 1 matrices? What's the distance to the matrices who have rank less than or equal to n minus 1? Using the theorem. See if you can parse the theorem properly, or decode the theorem properly. If you decode it, what's the distance? The distance to the rank n minus 1 or lower matrices is going to be sigma n. Right? It'll be sigma n squared to the 1/2. Right? It'll be sigma n. Right? That's what the theorem says. The theorem says the distance to the guys of rank less than or equal to n minus 1 is going to be the sum of the squares of the singular values above n minus 1. Well, there's only one singular value above n minus 1. It's this one. Okay. So what does that tell you? The rank that gives us actually an interpretation of this sigma n. The rank n minus 1 or lower matrices are the non-invertible matrices, right? If you rank n, you're invertible. If your rank is less than n, then you're not invertible, right? So this is basically the distance to the non-invertible or singular matrices. Right. The matrices of rank less than or equal to n minus 1. That's the same thing as saying the singular matrices, right? And so the sigma n you can think of as a distance, right? A distance to the non-invertible matrices. And what we see is that, if we could create a matrix, we could create the closest non-invertible matrix to our invertible matrix by using all the guys down to sigma n minus 1. Right? If we used sigma prime if we took sigma prime to be this matrix, then that would be the closest non-invertible matrix. Closest non-invertible matrix. Just to give you some interpretation.
What's the advantage of finding a non-invertible matrix?
I don't know. It's just interesting. I think more important than that is all this is giving us is just an interpretation, basically. Like, what do these sigmas mean? Right? So this is the distance to the non-invertible guys. Yeah, more important than that is that we can get we can find the rank whatever matrix that's closest. Right? So that's a compression problem. Okay, so now let's see if we can get this. We'll never do the evaluations again. Well, there's still one more day with the evaluations in the last. So let's see if we can.
If your wife goes into labor,
Then there's no evaluations. Well.
YOLO.
Well, let's get through this then. Let's get through this. Maybe it makes sense to do the evaluations because I don't think we're not going to finish the proof of this. So okay, let's do evaluations. No, forget it. I want to go. Sorry.
Living life on the edge.
That's me. Okay, so here's the thing that we're trying to prove, right? That if something solves, if there's a solution, then this is the distance of A to that solution. Okay? If there's a solution, then there's a distance of A to that solution. And so here's the proof. So we're going to do something sort of very illegal. Okay? So assume there exists a problem. There exists a solution to the problem. Okay, assume there exists a solution to the problem star, and apparently it's possible to show that a solution exists without finding the solution. Okay. So I mean, it's possible to show that, but it's hard. So this is a hard problem. So the author of the book says, you know, we could show this, but it would take us too far afield. So we're just going to take this as a fact. Okay, it's a fact. There actually exists a solution to the problem. Okay, let's call it solution X. Okay. We know that the distance of A to X, right, is minimal, so it's less than or equal to the distance from A to A prime. Right? A to A prime, which we just saw was this. Right? This thing is minimal, so if we take any other matrix, then it's going to be the distance is going to be greater than or equal to. Right? So. Right, this is minimal, and so that tells us that this distance is going to be less than or equal to this value. So it suffices to show then that the distance is greater than or equal to this thing here. Right, we've already noted that it's less than or equal to. If we show it's greater than or equal to, then it must be equal to. So that's our claim. So that's what we're gonna suffice to show the claim that this is greater than or equal to that. Okay. So let's prove that. On the first move, step one. First thing we're gonna do is we're gonna simplify this expression. Using the singular value decomposition. Okay. You say, okay, well, let's say that x equals Q omega P transpose is a singular value decomposition of X. And so we know that every matrix now has a singular value decomposition. Let's use it. Let's take the singular value decomposition. Okay. Now let B equal QT AP. So that A equals QB PT. So we create this new matrix out of A. Okay. We create this new matrix out of A in such a way that A equals QB PT, where X equals Q omega PT. Okay. So you see the advantage of doing that is that then if we look at this thing that we're trying to simplify, well, that's going to be A minus X. The Frobenius norm of A minus X, and you see what we're going to do, right? What are we going to do? We're going to peel off the orthogonal matrices. Right? So this is going to be B minus omega. So that's step one. Let's notate omega as, remember, X is a rank K or less matrix, right? So you have this K by K non-zero, you have this K by K diagonal matrix here, and then you've got zeros everywhere else for the omega. Right? So let's notate this for the K by, this is the K by K block of X. I'm going to do the same thing for B. We're going to split it up into blocks of the same size. We call them B11, B12, B21, B22. So this is again K by K matrix. Right. X is we call M by N. Okay. So just some notation. Okay. Then if we look at this thing that we're interested in, right? We're interested in this thing, which we've reduced to this thing, right? Then what this is, we're going to express it in terms of this notation. This is going to be the square of that plus B12's Frobenius norm squared plus B21's Frobenius norm squared plus B22's Frobenius norm squared. Okay. So just using the notation, yeah, Haley.
How did those switch? What's that symbol?
Omega?
Omega minus B instead of B minus omega.
It doesn't matter because we're taking the norm of it. So, right, the norm, if we take the norm of negative a matrix, that's still going to be the same as the norm, the Frobenius norm of the matrix. So it doesn't matter. If you like, I can write B11 minus omega k. It's the same thing. Okay. So I think this is step 2. Analyze the Frobenius norm. Analyze that thing that we've just reduced to. Okay. So we're looking at this thing, and we've broken it up into pieces here. And what we're going to see is that each of these pieces has to be equal to 0. Okay. We shall see that each of the first 3 pieces has to equal to 0. Okay. And the last piece will give us what we want. So here's the first claim, that B12 actually is the 0 matrix. Okay. That this piece here has to be the 0 matrix. And the proof is by contradiction. Suppose not. In that case, if you take the matrix Q B11, B12, 0, 0, PT, then Y has rank less than or equal to K, and the distance of A to Y squared is going to be B11 squared plus B22 squared. Which would be strictly less than B minus omega's Frobenius norm. And that's a contradiction. That's a contradiction because X was supposed to be the minimal norm. Right? X was supposed to be the one whose distance to A is minimal. But here, we've created something who's got rank less than or equal to K, and it's closer. It's strictly, right? The distance between A and Y is strictly smaller than the distance from A to X. That's not possible, right? Assuming that X is a solution. Okay. Is that clear? Anyone confused with that? Right? Say, right? Suppose that this thing is not equal to 0. If we create this new matrix, then this matrix has rank less than or equal to K, and the distance between this one and that one, by the same sort of reasoning as before, is going to be, well, it's going to be the Frobenius norm of this thing in the middle. That's to say this, right? But the Frobenius norm of A minus X equaled this thing, which we saw was squared. It was this thing, right? Right. So then we end up with something here, right, which is strictly less than. Right, it's strictly less than B12 squared plus B21 squared plus B22 squared. Right, which is plus this thing squared, which is this. Right? So we'd end up with something strictly smaller. Right? Right? Because the point is that this is bigger than 0. Right? So we're adding on something bigger than 0, it gets bigger. Okay? So B12 has to be equal to 0, and similarly, you create another matrix that would make things wrong, and you see that B21 has to be equal to 0 also. Okay, give me 1 second just to, sorry to keep you a little bit over, but let me just finish up this section by showing that, so right now we've seen that this is 0 and this is 0. Okay, so let me show the last part, that this guy is also going to be 0. And then there'll be one more step left that we'll get to next time. Okay, so last claim that omega k minus B11 is the zero matrix. So proof, take Z to be the matrix Q B11000 PT. And we'll play the same game as before, right? The distance of A to Z squared is going to be B22 norm squared. Right. Again, we're going to say the same thing, right? This is if we throw in say that omega k minus B11 is not equal to 0. Right? So, but it's not equal to 0. In that case, this thing is strictly bigger. This thing is strictly bigger, and we end up with the distance of B to omega squared, which is to say the distance of A to x squared. Right? So again, we'd end up with a contradiction. Same argument. So each of these pieces is going to be 0. And what that tells us is this, that thus B looks like this. Omega k 0, 0, B22. Okay. And we also have that the distance of A to x is the distance of B to omega, which is the size of B11, B22, excuse me, squared. And so there's one last thing we need to do is we'll see, next time, we'll see that this thing is bigger than or equal to this. Is bigger than equal to this. Okay, and that will finish it up for us. Okay.